Alright, so let's talk about implicit differentiation. Um, when y is a formula which is either not given or not easily obtained or differentiated, but an equation involving y is given, then it may be possible to find y as a function of x, at least in principle. Hence, we may theoretically calculate dy dx despite of a lack of an explicit formula. Just a little shout out here. This may, the answer to that is ultimately supplied by what's called advanced calculus. Advanced calculus being the study of the theoretical structure of calculus, in particular of several variables. If you take advanced calculus with me, Math 332, I would try to give some further detail on when that the answer to when this may is possible. For the moment in Calculus 1 and Calculus 2 and Calculus 3, we just assume that we're working in a situation where it's possible to do it, and we don't concern ourselves too much with the existence, and it won't get us into trouble unless we are mathematicians and we're just interested in getting into trouble. So, and since we're not that, we'll be fine. So the quintessential example, y equals x to the x. So how do you differentiate that? Well, it's not a power rule, it's not an exponential, so it's not a composite of a power, it's not a composite of an exponential, it's kind of both at the same time. So what do? Well, standard calculus 1 technique here is just to take the natural log of both sides. If I take the natural log of both sides, I get the natural log of y equals the natural log of x to the x. But we know our properties of logs, so we know that that's x ln x, right? Aha, well now I have an equation, right, which involves y and x in this way. So then I differentiate implicitly, both sides, with respect to x. That gives me 1 over y, dy dx, right, equals to, derivative of this is the natural log of x plus x over x by the product rule. So, consequently, we find that the derivative with respect to x of x to the x is exactly equal to this thing, which is 1 plus the natural log of x, right, times y, but y is x to the x. And so this is kind of a neat one in some sense. Oh no, it's not green. For those of you it's bothering. Here it just so happens we were able to calculate an explicit derivative using implicit differentiation. We did this before when I calculated the derivatives of some inverse functions as well, all right? But more generally, that's not what we're after here. We may have to content ourselves with a derivative formula which is also implicit. Implicit just means that you don't have just a straight formula for y as a function of x. It's implicit. It's somehow wrapped up in some equation which maybe involves both x and y, or who knows what else. So here, this is a quintic. It's a fifth order polynomial in y. Generally speaking, you can't just solve these things, all right? It's been proved for a while now. Abel, was it Ruffini? Galois kind of gave the ultimate answer to this back in the early 19th century. But anyway, sufficient to say that there's not a nice formula for like unwrapping this as y equals blah. So pretty much we're stuck with what we have to do. So we're going to differentiate both sides implicitly. This gives us 5y to the fourth dy dx. And so some of you might remember, can't I just write y prime? Well, yeah, I suppose you can. But I prefer dy dx for a simple reason. It's really easy to lose a prime. It's pretty hard to lose a dy dx. So if you write dy dx, yeah, it's a little more trouble to write, but it's a lot harder to lose. If you write y prime, it's so easy to change a y prime to a y, especially if you're not very good in your the precision of your writing. All right, so 3x squared. And then all I got to do is go, aha, 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 there it is everywhere. Solve for it. In other words, algebra. So dy dx is 3x squared divided by 5y to the fourth plus 16y cubed plus 6y plus 1. And there you have it. That is y implicitly as a function of x. And you can use this even to find the equation of a tangent line to the curve. at a point, even though you can't solve for y explicitly as a function of x. Let's see here. Let's just do that for kicks. What's a point on this? I don't know. Let's try to find a point. Well, if I put y equals to 1, what do I get? So let's see. Y equals to 1 gives me 1 plus 4 plus 3, 7, 8, 9. Oh, cool. Y equals to 1 gives me 9. Equals to x cubed. So if I look at the point cube root of 9, comma 1, that's a point on the curve that's given by this equation, right? And then so the slope to so I don't know, I mean, I can't even, maybe it looks like this. Who knows? Right, so there's a point on the curve though. All right. Cube root of 9, comma 1. And so to find the slope of the tangent line to the curve, right? This guy. What's the slope for this? So this is basically y is equal to 1 plus m times x minus cube root of 9, right? What's m? Well, m is given by this when you plug in the point. So m is equal to dy dx at the point cube root of 9, comma 1. And that is equal to, let's see here, 3 times the cube root of 9 quantity squared divided by this stuff down here, which is just 5 plus 16 plus 6 plus 1. Otherwise, it's known as, let's see here, 23, I think 28. Anyway, I made it. Who knows? That could be my arithmetic on these sorts of things. Always questionable. By the way, if I ever make a arithmetic mistake in class, I always welcome your corrections. I am human, believe it or not. So there's all you do is just plug that number up in there, and there you go. That is the tangent line to this curve that I can't even graph. And that's part of the power of calculus, right? Being able to analyze things that we can't just plot points for and stuff like that. One more explicit differentiation, maybe two more explicit differentiation examples. Another, see, example 3. This is sort of standard fare, something like x squared y plus the 2 to the xy equals to 7. There. That's weird. Find dy dx. All right, so implicitly differentiate this, we get what? D dx of x squared times y plus d dx of 2 to the xy, right, equals d dx of 7. Of course, this is 0, right? That gives me 2xy plus x squared dy dx. Then by the chain rule, well, the derivative of 2 to the something is natural log of 2 times 2 to the xy times the derivative with respect to x of x times y. That's all equal to 0. Of course, this is a product rule again. Product rules galore in this thing, right? 2xy plus x squared dy dx plus the natural log of 2 times 2 to the xy times, what is this? Well, that's y plus x dy dx equal to 0. All right. Now, finishing below, solve for dy dx. All right, so this guy and this guy, I can solve for it. Dy dx equals to what? So what I do is I just take everything that doesn't have dy dx to the other side, which is, you got yourself minus 2xy, product of this and that, so minus the natural log of 2 times 2 to the xy, and there's a y, I'll put it out front. So that's this times that, right? That's all that moved to the other side. Then I would be able to factor out in front of dy dx an x squared, and then the product of x and that, so plus the natural log of 2 times x times 2 to the xy. And there you have it. That is dy dx for that curve defined by that algebraic equation. So this is implicit differentiation. Now, of course, the principal application of one of the principal applications of implicit differentiation, important application is what? I suppose there are many, but the one that comes to mind right off is the topic of related rates, right? So related rates, basically, the point is you're given some algebraic, or I mean, it could be an exponential. I mean, when I say algebraic, I mean, it really just means there's a formula, all right, that relates some variables. Algebraic. That's too specific. Formula, which relates some variables, all right. These variables are typically physical in nature, and so that means that you can view them as functions of time, right? So, for example, and there's, this is a very popular thing to do a few lectures on. Suppose you have a car, right? And it is stuck on this track, right? It's supposed to be a car. All right, anyway. And the equation of the track happens to be x squared plus 4y squared equals to 1. So it's like an oval, right? Then you can ask the question, how is the x and y velocity related, right? It's pretty simple. All you got to do is differentiate this with respect to time, right? And the way you do that is implicit differentiation, right? Because you don't know x and y as functions of time. All you know is that they are functions of time. But that's no problem because we know calculus, and so we got ourselves 2x dx dt plus 8y dy dt equals to 0. And so the relation between dx dt and dy dt is simply that, right? So I guess I can solve for dy dt. dy dt, right, is equal to what? It's equal to minus 2x dx dt divided by 8y, except for when y is equal to 0, right? Actually, the kind of interesting thing, I don't know, I mean, that's one answer. This is in some sense a better answer, right? Because this doesn't need to be qualified. This is true at all points around the oval, but this is only true when y is not equal to 0, right? Because, in fact, this actually kind of is kind of a dead giveaway for when the implicit differentiation fails. If you think about it, it's kind of clear why that happens here and here in terms of y. You can't make y just a function of x, right? Because it's necessarily y is not a function of x here. It fails the vertical line test. So that's kind of the underlying reason for that. But anyway, let me not get off topic here. So there's a few examples of implicit differentiation. Doesn't come up too much in Calculus 2, but it is an important skill that you should know. The next thing we'll talk about in my lightning review of Calculus 1 for you guys will be a bit on minimization, maximization, optimization, and how to graph with calculus. Graphing with calculus is important because it's one of the chief tools we have to find bounds on functions. Thanks, guys.